yesterday we ended class talking about the stability of different alkenes. And earlier with this worksheet that we handed out last week, we had said that this compound, 1-bromo, 1,2-dimethyl cyclohexane, has the potential to make 3 different alkenes. Out of those 3 different alkenes that are possible, I want you to rank them by which is most stable. So I've given them as A, B, and C. Let's say least stable on the left, most stable on the right. I want you guys to take a minute to think about how to rank them, and then I'm going to ask you to share.
Does this guy that's really stable in tetra count if it's cyclic or not so much?
Well, okay, I think your question would be answered by saying, does this change the nature of the alkene?
Yes. No.
I can't see how it did.
Okay.
Because it's still got all of the same groups essentially bonded to it. The difference is, are these carbons bonded to each other?
Right, true, okay.
So no, being a cyclic alkene or being a linear alkene does not impact its stability.
No. Oh, from least stable, yeah. I was like,
So you guys agree on this? A, B, C. Anybody else?
wait. Or B, no. C. Yeah.
B, A, C.
Oh my gosh, I'm getting confused.
So
Or CAB.
Or CAB.
Or CBA.
Okay, these are all the options, yes.
I think it's BAC.
Out of the 2 that you guys were initially giving, it was you were confident that C was the most stable. Can you tell me why?
Because it has 4.
Good. Tetra substituted. That's as substituted as it can get. And the more substituted it is, the more stable. Remember that what makes a pi bond reactive is the fact that it is the highest energy electrons and it is the lowest energy available spot for electrons. So pi bonds react the most. What's going to stabilize that pi bond is shrouding it with electron density so that new electrons can't get in and the electrons that are there don't want to leave. So more substituted, more stable, we should be able to say then if either A or B is more substituted, it's more stable. The fact that you guys are kind of debating it makes me think that you think maybe A and B are the same degree of substitution. Is that true? They're not the same degree of substitution?
I thought B was try, A was die.
Is there any way to confirm?
Yeah, but if B was try, it would be try. Thank you.
You're welcome. You're welcome. Do you guys like a worksheet?
Yeah, that would be great.
Is it on?
It is.
Carbon's coming off it.
Can you prove it? What is the substitution of A?
Try.
A is tri-substituted. Prove it.
Because it has carbon going this way, carbon going that way, carbon going that way.
Great. There's 2 carbons of the alkene. One carbon of the alkene has 1 carbon group. The other carbon has 2 carbon groups. 3 carbon groups coming off of the alkene, tri-substituted. B, di-substituted. And we said there were 3 different types of di-substituted. There were cis-trans internal di-substituted. And then there's this terminal. Is this cis-trans internal or is it terminal?
Terminal.
It's terminal. That di-substituted has both groups on one carbon, and the other carbon is a CH2. So which of our answers is right? BAC. Di-substituted, tri-substituted, tetra-substituted. Great. Now, I said that we were going to talk about a very similar trend with carbocations. We've already established that hyperconjugation stabilizes that positive charge, or the way that I refer to it is moral support. That carbon is lacking electrons, and the more neighbors that it has that have a lot more electron density, the more shrouded that positive charge is, the more stable it is, the less likely it is to attack, right? I mean, imagine taking a magnet and then wrapping it in a sheet of other magnet. Now how likely is it to attract other magnets to it? A lot less likely. That's the idea of shrouding the carbocation with electron density. So our least stable possibility is a methyl carbocation. A carbon that has no other carbons bonded to it. It has no hyperconjugation. It can accept no electrons from any other group because there are no groups with electrons next to it. Then the primary carbocation, the secondary carbocation, and the tertiary carbocation. Are you guys okay with these abbreviations? I'm using C+ to represent carbocation. And we've been talking about regiochemistry terms like this for a while. Yeah, primary, secondary, tertiary. So why am I not listing the quaternary carbocation as the most stable? That is oxymoronic, yeah, which is sounded worse coming out of my mouth than it did in my head. That's an oxymoron to say a quaternary carbocation, because quaternary means what? 4 bonds, 2 carbons. And a carbocation has how many bonds? Only 3, whether it's to other carbons or not. So a carbon can't both have only 3 bonds and have 4 bonds to other carbons. There is no quaternary carbocation. This is not the end. This is the most stable carbocation without resonance. I've said this a few times. Do you guys know what resonance gives to a molecule? What it provides to a structure? Yeah, resonance stabilizes radicals. It stabilizes positive charges, stabilizes negative charges. Resonance delocalizes electrons, which makes electrons more stable. So, if I have a carbocation that is conjugated, do you remember what conjugated means? We talked about this yesterday, didn't we? That's not a vowel, that's a verb. But we conjugate verbs because they're different words related to each other. We have conjugate acid and conjugate base, which are different structures, but they're related to each other. So if I have a conjugated structure, different atoms, but they're related to each other. That's the connection I want you to have. Conjugation is a relation. Related by what? Related by the movement of pi electrons. So most stable without resonance. Now, we'll look at the conjugated carbocations because this will always stabilize it more. A primary carbocation that is allylic up to a tertiary carbocation that is allylic. Let's talk about what allylic is. I wonder if any of you remember. a regio term that we talked about much earlier in the semester, or if you've been looking at that functional group table that I've given to the class, you maybe have seen allylic alcohol, allylic halide, allylic carbocation. The allylic group is this. 3 carbons. 2 of them are in a pi bond, 1 of them is not. If I placed an OH on the right here, that's an allylic alcohol. It's not on the alkene, it's adjacent to the alkene. If I put a halogen there, it's an allylic halide. If I put a carbocation there, it's an allylic carbocation. And that carbocation is in resonance. The pi bond is delocalized across all 3 carbons. The positive charge is not in one place or the other. Remember what stabilized the carbocation was shrouding it with electron density. Because I've got this positive charge localized in one spot, I need to make it less of a magnet if I want it to be more stable. You know how I can make it less of a magnet? Spread it out. It's not a positive charge in one place anymore. It's a half positive charge in 2 places. That's a weaker magnet. That's more stable. How can I make it even more stable? Give it even more resonance. So after being conjugated in an allylic system, we can see increase in substitution in a benzylic system. Do you remember what benzylic is? The ring, it definitely involves the benzene ring. Allylic is adjacent to an alkene. Benzylic is adjacent to benzene. Benzylic, confusingly, is not on a benzene carbon. Benzylic is adjacent to the benzene. The benzylic position is off of the benzene. Now, in the resonance form we had on the left, if you're looking at the electron arrow pushing, electrons move from the pi bond to the positive charge, leaving in its wake a positive charge on a different carbon. Let's do that with the benzylic position. A pi bond moves toward the positive charge, leaving in its wake a carbocation in a new position. Here's position 1, 2, 3. Pi bond moves over. And now I have a positive charge in the ring. That's nice. But why is that more stable than being allylic? Because allylic only had 2 resonance forms. Benzylic can keep delocalizing this positive charge. More resonance, more delocalization, more stable carbocation. Stability always increases with substitution until resonance, and then it starts over. You guys okay with this? A primary allylic carbocation is more stable than a tertiary non-conjugated carbocation. A primary benzylic carbocation is more stable than a tertiary allylic carbocation, increasing resonance, increasing stability. All right, those are our carbocations. Carbocations are vacancies. To clarify, a carbanion is not a vacancy. A carbon with a lone pair has a full octet. But a carbon with a positive charge is lacking in octet. So I want you to think of this as a hole that things can move into more than something that moves around on its own. It is a vacancy. I'm going to give an analogy to think of a carbocation as a spot in line ahead of you. You can move things into it, and you can leave a new hole in your wake, but you can't move a positive charge. Good?
So is it missing a electron pair, or is it missing the orbital?
An orbital is a mathematical equation. So it's not missing a mathematical equation. But the mathematical equation that defines how an electron would behave has no electrons behaving like that. It's an empty orbital. So it is lacking electrons there, but there is a place and a mathematical equation that describes electrons that could occupy it. Does that make sense? Okay. So we have this idea about the stability of a carbocation. So we need to talk quickly about how carbocations rearrange. If a less substituted carbocation forms, adjacent to what would be, this is such a silly sentence, a more stable carbocation. This is the deal. If a less stable carbocation forms adjacent to what would be a more stable carbocation, then the carbocation will rearrange and it will find that lower stability. On the worksheet that you have, we talked about how two different carbocations are possible. We said one of those carbocations is this less stable primary carbocation. The other possible carbocation is the more stable tertiary carbocation. We said if you had enough energy to make the primary carbocation, you already had enough energy to make the tertiary carbocation. So the tertiary carbocation is the one that will form. If you get enough energy to make the primary, you've already made the tertiary. Okay, but what about that odd % of the time where the primary carbocation does form? That's a less stable carbocation adjacent to a position that would be a more stable carbocation. And because these molecules are always in motion, their bonds are vibrating, wagging from side to side, that means that the electrons can actually find their way to slope down into a more stable position and leave in their wake a more stable carbocation. So if this carbocation forms on top, then the hydrogen on the tertiary position would shift over with its electrons to form a more stable carbocation below. Or in other words, this energy diagram, think of it as three-dimensional. If you somehow took this higher energy route and you get down to this intermediate, the most stable pathway is actually to come over here to a more stable carbocation. Think about hiking in the mountains. You've gone up a hill, and the best route down now is actually to just cut over this little pass to a lower hill. That's what the carbocation is doing. This type of rearrangement, where a hydrogen shifts a carbon, shifts over by a carbon, this is called a hydride shift. What is hydride? God, I got to tell you, I'm so glad this isn't called like the Jacobson shift or something, which would tell you absolutely nothing. But it doesn't tell you much if you don't know what hydride is. Any guesses? A hydrogen? So why don't we call it hydrogen shift? When you say hydrogen, do you mean proton, nucleus, and electron shifts? What is the IDE of hydride? What is that meant to tell you? IDE. Have you ever heard of any other words that have IDE as the suffix? What type of ion?
Charge.
Ions are always charged. Chloride, hydroxide. What do those all have in common? Bromide, iodide, negatively charged. Hydride is not a hydrogen ion because we typically think of the hydrogen ion as H+. Hydronium, H+. Hydride, H-. How do you get H-? Hydrogen with a pair of electrons. Because hydrogen is taking the bonding pair and moving to a different carbon, it's essentially acting as H-. And I do want you to think that that's weird. Who owns the electrons of carbon and hydrogen? Carbon. And yet we're seeing hydrogen scooch over with the lone pair. So we're looking at a hydride shift. That's one example. And here's another. So that was a primary carbocation to a tertiary carbocation by means of a hydride shift. What about this process? If this structure were to form a carbocation, let's say that it accepts a hydrogen ion, it's going to bond to a hydrogen. Which of these two carbons is more likely to bond to hydrogen? Which of these two carbons is more likely to lose the electrons entirely and become the carbocation?
Would the first one be more likely?
Sorry, I gave too many options. So you have to more likely to what?
Would be more likely to accept the hydrogen.
More substituted, meaning this one.
Yeah.
More likely to bond to the hydrogen,
Yes.
leaving a carbocation on the less substituted. Rowan? What?
I was going to say, isn't it the reverse of that?
What position would be more stable holding the carbocation?
The more substituted carbon?
The more substituted. What about partial charge? We talked about predicting partial charge here yesterday. What partial charges do we see? On this carbon, partial positive or partial negative? Not formal charge. Formal charge is 0. It has 4 bonds. Partial charge, meaning how electrons are shifted. Yeah. I know it. But we saw yesterday that there is resonance possibilities, and that one resonance possibility is more likely than the other resonance possibility. So because there is resonance, there is a dipole.
Negative.
Partial negative here, because there's less electron density to repel that lone pair. And partial positive here, because it is more stable with less electrons. So when you are making a prediction, which of these carbons will bond to the hydrogen? The one that controls the electrons bonds to the hydrogen. Which of these will become the carbocation? The one that is more stable with a positive charge. 2 cations are possible. 1 cation forms.
Wait, where was the less electron density?
Partial negative has more control of the pi electrons. Partial positive has less control of the pi electrons.
So less density has more control, which is the partial.
No, I'd say that's more density of electrons. Electrons are negative.
Yeah, but how is it more density if it's like not surrounded by as many groups?
The pi electrons are not equally across both carbons. The pi electrons find themselves here more often.
Okay.
So there's a higher electron density here. Does that make sense?
Yeah.
Let's.
It makes sense when you put a dipole there.
Yeah. Well, I want you to predict that. I want you to be able to expect that.
So does this have anything to do with substitution? No, this just is kind of like a little.
Actually, this is going to set us up for addition reactions. It's actually not as useful for substitution. Why did you ask about substitution?
Oh, just because he said earlier that one was more.
Oh, sorry.
Yeah.
Okay, actually, here's a good learning moment. Substitution is way overused. We said substitution is a type of reaction. One group substitutes another. We've also been using substitution to say primary, secondary, tertiary, mono, di, tri, tetra. So yes, partial charge does have to do with degree of substitution of the carbon. Less substituted carbon, more negative. More substituted carbon, more positive, which agrees with what we're seeing here. More substituted, more positive, because it can stabilize it better. 2 carbocations were possible, 1 carbocation forms. Let's analyze this carbocation. What type are we looking at? First of all, it's not conjugated, it's just a regular carbocation. What type here do we have? Secondary carbocation. The carbocation carbon is bonded to 2 other carbons. What adjacent possibilities do we have? Secondary carbocation, what's adjacent to it? Yeah, the primary carbon on the left, we already said would have been a less stable carbocation. That's why we didn't form the carbocation there. But there's a tertiary carbon to the right. We could call that a tertiary beta carbon. Would that be more stable as a carbocation?
Yeah.
It would be. And so it will. As if just going down a little water slide, the energy that it takes to rearrange is so small. It prefers this rearrangement. So this carbocation forms, yes. And then this carbocation rearranges. Let me add some of the electron arrows. Pi bond protonates, hydrogen shifts. What does it leave in its wake? It leaves a new positive charge. I feel like this positive charge is crazy. Think of this as a hole in front of you in the TSA line, and that hydride has just stepped into it and has left behind a new vacancy behind it. The molecule has rearranged. A hydrogen that was originally on this tertiary carbon is no longer on that tertiary carbon by no fault of the reaction, but because, or the reagents that have been provided, but because of the carbocation.
My first question is, would we see that as an intermediate then? And my second question is, would the third structure then be the most stable of the, I guess, structure?
So this can't be isolated. This rearrangement occurs very quickly. So rather than isolating this secondary one, we'll find that this forms very, very fast and is essentially the carbocation intermediate. That doesn't rule out the odds. There's some odds that this carbocation still reacts, that something reacts with it before it's able to go through a rearrangement. But the rearrangements are very fast. This step requires 2 molecules finding each other and reacting. The hydrogen ion and the alkene have to run into each other. But this doesn't require any molecules finding each other. This can happen just because of that vibrational energy a molecule has. So it happens very quick. This is what we would see moving forward in the reaction. The other type of rearrangement is a methyl shift. Although it doesn't have to be methyl, the examples that we'll see in class are methyl. It can be an entire alkyl shift. The larger the alkyl group, the harder it is to shift, because the more mass that has to move in that rearrangement. If a hydrogen can shift, a hydrogen will shift. So the only time we'd see a methyl shift is if there's no hydrogen that can shift. So let's take a similar structure, but take that tertiary carbon with 2 methyl groups. Let's make it a quaternary carbon with 3 methyl groups. We've just removed that tertiary hydrogen. Once again, I'm going to form the most stable carbocation that my alkene can form. Once again, that's the more substituted carbon of the alkene, becomes the carbocation. We stop and analyze this carbocation. Once again, it's a secondary carbocation, but now it's adjacent to a quaternary beta carbon. How stable is a quaternary beta carbon? A quaternary carbocation?
I would assume it's more stable, right?
It doesn't exist.
Oh, okay.
Right. We mentioned that it doesn't exist because it can't have both 4 bonds to other carbons and only 3 bonds to give it a positive charge. So there is no quaternary carbocation. That's because one of its methyl groups will have to shift. And if it loses a methyl group, it loses a degree of substitution. So really, this has the potential of becoming a tertiary carbocation. Is that more stable or less stable than what I already have? That's more stable. So it occurs. The methyl group shifts over in the same way that we saw the hydride group shift over. Leaves in its wake a new carbocation, this time a tertiary carbocation. Takes more energy to move than a hydrogen. So if there's a hydrogen shift, a hydride shift possibility, a hydride shift occurs. If there's no possibility for it, that's the end. If you look at the top of this worksheet, the one that we're still finishing, the one with the reaction energy diagram, and you look at the top right, we had that structure with OTS coming off of it. How many alkenes did we say were possible to form from that structure? 2. We said there were 2 alkenes possible. But what if this process formed an alkene by way of a carbocation intermediate? Now you see that same structure is present again at the bottom of the page. If that structure forms a carbocation, I understand we're going a little bit in a different direction here. Rather than starting with an alkene and making a carbocation, we're making a carbocation on the way to an alkene. If this group forms a carbocation, would it rearrange? Why?
More stable options adjacent.
Directly adjacent, there's a more substituted carbon. This secondary carbocation can be predicted to rearrange by way of a hydride shift.
Are we looking at the thing on the bottom?
On the bottom. We had this same starting material at the top, and we said that there were 2 alkenes that could be made from this. Now we're looking at it again on the bottom, and we're saying if this formed by way of a carbocation intermediate, there's actually a new alkene that could be made. A rearrangement allows for a different elimination to occur. At the top, did we predict that this compound could make a tetrasubstituted alkene? We didn't, because we didn't consider how a carbocation might allow the compound to rearrange. Another way of looking at this. We said earlier that this compound could make a double bond with the carbon of the leaving group and either carbon adjacent to it. So how do I end up making an alkene without using that carbon? How do I end up making an alkene where there was no leaving group? How do I end up making an alkene and not using the carbon that lost the leaving group? The structure has rearranged. And we'd be able to prove this, right? If you're running this in lab, take the product, put it into the NMR, and look at the number of proton NMR signals that you get back and their integration and their splitting patterns, and you can prove which of the structural isomers you made. You can prove whether it's rearranged or not. In fact, NMR is super useful exactly for that. NMR allows us to determine whether a structure is rearranged or not by looking at where the new hydrogens are. Okay, a slightly different version. This time, the carbocation will form adjacent to that quaternary carbon. No hydride shift to make it more stable. Instead, a methyl shift to make it more stable. Rowan.
Could you just draw the arrows going from like on the last one we did, from the carbocation to the alkene?
Could I add the arrows here?
Yeah.
Sure. Why don't I add arrows to the first step as well, which is not as hard, but the bond breaks from carbon-oxygen just to oxygen. What I haven't done here is shown a base. So what I'll use is the TSO- as my base. You can see that I need to lose the hydrogen that was assumed here. If I need to show that bond breaking, I can't assume it. I have to show it. So a base deprotonates my carbon and allows for the CH bond to become an alkene. We're going to look at that mechanism more in Unit 5, actually, next week. Wow, exciting. All right. By the way, there are other ways that structures can rearrange by carbocation rearrangements. This is an example of an alkyl shift that provides ring expansion. It doesn't actually improve the stability of the carbocation. Goes from secondary to secondary. In fact, this secondary carbocation is likely to rearrange again to the tertiary position. So what is the energetic preference for this alkyl shift? It minimizes angle strain. It gets rid of those tight bond angles in the four-membered ring. It alleviates it by making a more stable, less strained five-membered ring. This is, in my opinion, very fun and cool, but it's not something I'll have you guys do in mechanisms or have to make predictions on.
Larger rings are more stable than kind of smaller rings, generally.
The six-membered ring is the most stable ring. Below six-membered is more strained, and above six-membered is more strained. Six-membered is really the sweet spot, which is why you see, cyclohexyl rings all over the place.
Sorry, on the second reactional worksheet, you didn't draw a double bond
Oh,
there. Where did that come from?
on the second reaction,
Yeah.
here,
Yeah,
I have a double bond.
not on the double.
Oh, well, that's because I didn't finish it.
Oh, okay.
This carbocation that formed by the methyl group rearranging, that carbocation can form the same alkene as before. Okay, questions? We're moving in now to our section on alkene addition reactions. You guys will be expected to fill in the blank for one of three pieces of information. what starting material is needed, what reagent is needed, or what product is formed. Given starting material and product, I need you to be able to recognize what reagent completes that synthesis. Given the starting material and reagent, I want you to be able to predict what product is formed. Given the product and the reagent, I want you to be able to figure out what starting material was necessary. So there's 3 pieces of information to these alkene addition reactions. And I want you to be able to solve for the third given 2 of them. Okay? That's our first step into doing organic synthesis, is be able to solve for the missing 1 of 3. In Unit 5, we're going to take this a step further, and we're going to have a starting material and a product that are separated by some number of intermediates. And you should be able to sew together multiple synthetic steps to be able to get from one starting material to the final product. This is organic synthesis. So this is our introduction. 12 different reactions. On the worksheets, I've already given you the reagents and demonstrated some of its regio and stereo principles. And then I've shown what functional groups form as well. Does anybody need one of these? Did I get them to everyone? If you cannot name the functional groups on this worksheet, start there. Get to know your functional groups. I am 85% confident that all of these functional groups show up on that functional group table I gave you guys. And some are very specific, so I want you to be able to recognize them. What I'm going to go through first is I'm going to make a list, and I'm going to give you information about all of these, okay? First is HX addition, sometimes called hydrohalogenation, because that's what we're doing to the alkene. We're adding a hydrogen and a halogen. What I want you to notice about the reaction that's given, we're using that same alkene that I had listed earlier. What I want you to notice is that the halogen, X, shows up on a carbon that wasn't in the alkene. The HX that you might use is HCl or HBr or HI. More often, HCl and HBr. How did the halogen bond to a carbon that wasn't in the alkene? The structure must have gone through a rearrangement. How did the halogen end up where a hydrogen was? The hydrogen must have rearranged. So this reaction goes through a carbocation intermediate. It must. This is the only way for a rearrangement to occur. So this mechanism has a carbocation rearrangement. If this reaction produces a chiral center, the chirality formed will be random. Uh-oh. It's not dead, it's just dying. It's like only charging if the cable is coming out. In the example that you're given, 3-methyl 1-butene reacts with HX to form 2-methyl 2-halo butane. How many chiral centers form in the example that I gave you? 0. 0 chiral centers form. So you can't see in the example that I've given you, you can't see any of the stereochemistry. So I'm going to give you an example to highlight the random chirality. if we ran this reaction with 1,2-dimethyl cyclohexene, both carbons become chiral centers. So what is the chirality at those positions? Well, the hydrogen adds on one carbon, and it might add up or down. The halogen adds on the other carbon, and it might add up or down. Looks like syn addition, looks like anti-addition, not controlled by the mechanism. Because this has a carbocation intermediate, it means the hydrogen adds first and creates a chiral center. Then the halogen adds and creates a chiral center. The formation of a chiral center is not dependent on each other. So the two chiral centers that form randomly. It's neither syn nor anti-addition. It's random addition. Is that okay? That's a stereochemical term. So here's a term about the mechanism. Here's a term about the stereochemistry. Here's some information about its regiochemistry. Its regiochemistry is described as Markovnikov. What did we say Markovnikov's rule was? Silly. That's what we said it was. Markovnikov's rule is hydrogen adds to the carbon with more hydrogen. And we found that to be true. In the example that we had, hydrogen added to the carbon with more hydrogen. So it follows Markovnikov's rule. Reaction number 2, we're going to go clockwise. Halogenation. Or you can call it X2 addition. You can see that the two halogens, the halogens here are either Cl2, Br2, or I2. You can see that the two halogens bond to the same carbons of the alkene, which means the mechanism has no carbocation intermediate. We can't describe this as Markovnikov or anti-Markovnikov because there's no hydrogen being added. What we don't see, I didn't give this in the example, but this is an anti-addition reaction, meaning the two halogens will add one wedged, one dashed across the alkene. They add to opposite faces. And although we can't describe the regiochemistry as Markovnikov or anti-Markovnikov, there is still regiochemistry in the mechanism. We're going to go through this mechanism as well. There is an attack at the more substituted carbon. It's regio-specific still. More substituted, more positive. So a negative charge attacks more positive, more substituted.
Are there attacks at both carbons? Because they're both bonding with halogens?
There could be an attack on either carbon, but the attack will always happen on whichever carbon is more substituted. We're going to go through the mechanism, so I think this will make more sense when we come back to it. The next two reactions are actually sister reactions. Haloether and halohydrin. Haloether adds X and OR. Halohydrin adds X and OH. So you can see one of them is a reaction with a halogen with alcohol, and it forms an ether on the final product. One of them is a reaction with halogen and water, and it forms an alcohol. What's the question?
I wasn't here when you wrote that MS and R.
Oh, the mechanism, the stereochemistry, the regiochemistry. Yeah, that is very confusing if that's not made clear. One thing I'll point out is halogenation in some places is written with this on the arrow, THF. Do you remember what THF was? THF is a polar aprotic solvent, a lot like diethyl ether that we use in lab a lot. THF is just telling you nothing is going to happen because of the solvent. These reactions will write X2 with some alcohol or X2 with water. And the distinction is that alcohol and water do react as a way of solvolysis. THF does not react. I don't typically show THF because it's not relevant to the reaction. But alcohols are precursors to ethers. Water is a precursor to an alcohol. These reactions are reactions that we're going to learn, all 4 of these. Okay, moving on to the next diagram. Starting on the top right. Acid-catalyzed hydration. H2O and H3O plus. Oh, I'm sorry. There was information I forgot to give up here. No carbocation, anti-addition, and nucleophile attacks at more substituted carbon. Same exact information about halogenation. The difference between halogenation and these two, what attacks in the second step.
What's anti-addition again?
Let me give that to the class. Can someone explain what we look for to see anti-addition?
Isn't it just like one wedge, one dash?
Kind of. Although sometimes we did look at examples where it doesn't always look like it's one wedge to one dash.
Like R versus X?
Not always. Anti-addition, your alkene is flat. Anti-addition is where one group adds on one face of the alkene, the other group adds on the other. And this gives the appearance of being wedged and dashed, unless, of course, your compound can rotate, in which case you might not see it as wedged and dashed in every conformation. But when a reaction occurs, it adds the two groups anti, as opposed to syn addition, where it adds them to the same face. Acid-catalyzed hydration, H2O and H3O plus. Tell me what you know about it, based on other information that's already on the board, based on similarities that you see between its reaction and the ones up top. It adds an alcohol. It actually adds H and OH, which is why we call it hydration, adds an equivalence of water. But what about the mechanism, the stereochemistry, the regiochemistry? How do you know it has a carbocation intermediate? The OH added to a carbon that originally had a hydrogen. How could the OH be where a hydrogen was? The hydrogen must have shifted. There must have been a rearrangement. This should look exactly like the example you had for HX addition. Rearrangement occurs. So we know there's a carbocation. In terms of stereochemistry, it's exactly the same. It gives random chirality. And in terms of regiochemistry, it is once again considered Markovnikov addition. moving clockwise down to the bottom right where we have mercury acetate. This reaction has two names because it's two steps. Oxymercuration followed by demercuration, or as I typically call it, reduction, because that second step is reduction. Mercury acetate. Acetate is that 2-carbon carbonyl bonded to the mercury. Acetate is that ACO minus. Notice over the reaction arrow, for the first time, you are seeing two numbers. First, mercury acetate in water, followed by sodium borohydride, NaBH4. This is a reducing agent. It is the source of H minus. Hydride, H minus. Who owns the electrons between a boron-hydrogen bond? You'd think boron because everyone thinks hydrogen is the least electronegative. Hydrogen is more electronegative than boron, which is why this is hydride. The negative charge is because hydrogen owns the electrons and can leave with them at any time. It's a source of H minus, essentially. Elvira, you looked like you had a question before.
I was just not sure where you were at on the worksheet.
The one with mercury, Hg. Middle diagram on the bottom right.
Oh, these are all.
Two steps. So if you are solving this and you just write out mercury acetate with water and sodium borohydride and you don't say first, second, you lose points. Because those have to be done first and then second. One time I was cooking for my partner, who's an incredible cook, and I was just trying to do what he does when he cooks, and I cut up some tomatoes and I threw them in the pan on oil, and then I cut up some onions and I threw them in the pan on oil, and he said, "What the heck are you doing?" I said, "I'm making the base, the way you always do, onion and tomato and then spices," and he said, "You didn't put the onion in first. You put the tomato in first." Yeah, I'm just putting in the stuff and then I'm going to cook it. How does it matter what I put in first? And apparently it matters. The onions need a little bit longer to fry, and the acidity of the tomato changes the way that the onion gets cooked. Crazy. Who would have thought that the order you do chemistry in the kitchen matters? The order we do chemistry in the lab also matters. 1, 2, can't be ignored. If it's not first, second, it doesn't work.
So mercury is always first?
Yes. Oxymercuration followed by reduction. What else do we know about this? Well, it hasn't rearranged, so there's no carbocation. But the hydrogen has still added to the less substituted carbon. So this one has random chirality. It has no carbocation, but it's still Markovnikov addition. Why do I need two different Markovnikov hydration mechanisms? The benefit of having two acid catalyzed hydration provides carbocation rearrangement possibilities. If I want a carbocation rearrangement, that's great. If I do not want a carbocation rearrangement, I have a different set of reagents to do that. Do you see why having both is useful? Ability to rearrange, ability to avoid rearrangement. All right, on to the next one. To the bottom left, we see our sixth reaction, hydroboration, oxidation. 2 steps. There's partial charge character in this reagent, borane. The hydrogen is partial negative. The boron is partial positive. So if I set this up, to interact with an alkene, I should see alignment of my partial charges. Well, okay, I mean like alignment like magnets. Partial negative of my alkene should align with the partial positive of borane. Partial negative of borane aligns with the partial positive of the alkene. In our other hydration reactions, the hydrogen added to the carbon with more hydrogen. The hydrogen added to the less substituted carbon. Hydroboration oxidation flips that. It says that hydrogen attacks the more positive carbon, and the less substituted carbon attacks boron. So this gives us a reactive intermediate where hydrogen has been added and this BH2 has been added. This is where our second step comes into play. The basic aqueous hydrogen peroxide reacts with the boron group and substitutes that boron for an oxygen. There is no carbocation, no possibility of rearrangements. The stereochemistry is always syn addition. And this is considered an anti-Markovnikov reaction. Because Markovnikov said hydrogen always adds to the carbon with more hydrogen. And this reaction proved him wrong.
Is that HO minus?
It is hydroxide. Yep. Okay, so this reaction is syn addition. I want to give you an example that highlights how syn addition it is. 1-methylcyclohexene reacting first with borane, then with basic aqueous basic aqueous hydrogen peroxide. Oh man, it's a little cut off, sorry. Anti-Markovnikov addition, so the hydrogen added to the carbon with less hydrogen. Man, that's just a silly little way to memorize it. The hydrogen attacked the more positive carbon. The hydrogen attacked the carbon with the most substitution, the best partial positive. Is that really syn addition? What argument would an OChem 1 student have for saying that product is not a syn addition product? Does it not look anti? It does look anti, doesn't it? Syn addition and anti-addition describe the groups that added. Did that methyl group add in this reaction? Was that methyl group already there, or was it added? So don't pay attention to the stereochemistry of the methyl group. Pay attention to the stereochemistry of what? The hydrogen and the OH. Those are the two things added. Where's the H? It's assumed. Those pesky little assumed hydrogens will always get you. The H and the OH added syn. Do you see what I'm talking about, Gavin, with syn and anti?
Yeah.
Okay. Syn addition. We are going to learn the mechanisms for HX, X2, halohydrin, haloether, and acid catalyzed hydration. 4 mechanisms that we're going to learn. I can show you the mechanisms for everything else. I'd love to show you the mechanisms for everything else. But the mechanisms you'll be tested on are the first 4 up top and the first hydration, the acid catalyzed hydration. We're going to be going through those mechanisms even in this worksheet. I want to keep us going, though, through the rest of our reactions. Reaction number 7 on the top left of that middle diagram. This is diol addition. In fact, we can call it syn diol addition. This reaction, of course, has no carbocation. I do want to tell you what these reagents are, sorry. OSO4 is osmium. Tetroxide. That is OS. When I write it on the board, I know oftentimes it looks like O5O4. O5O4 is better written as O9, and I've never heard of it. OSO4 is osmium tetroxide. And it's written with this TBUOOH. That is a peroxide. A peroxide is that OO bond. So the peroxide plays a role in helping get some of the oxygens and the hydrogens into the reagent. If you don't use osmium tetroxide, then you can use potassium permanganate.
Is that what we used in the lab yesterday?
Yes, it is. In lab this week, you are testing for the presence of an alkene. And so you took some potassium permanganate, which is aqueous and doesn't mix well with organics. So you also mixed it with triglyme, which is a phase buffer. It helps mediate organic and aqueous. And you did syn diol addition in the lab yesterday, or today, or tomorrow, or whenever you're in the lab, or Monday. Okay. No carbocation. The stereochemistry is syn. And the regiochemistry doesn't really have anything important, but we can say it forms a vicinal diol. Do you remember what vicinal tells us? I want you to hear vicinal and think vicinity. 2 groups that are in the same vicinity. They're on adjacent carbons to each other. They're not geminal, they're not twins, but they are vicinal.
So 2 alcohols on the same carbon?
Geminal, 2 alcohols on the same carbon. Vicinal, what do you see? 2 alcohols on adjacent carbons. 2 alcohols in the same vicinity. Is that making sense, Gavin?
Usually when I think of vicinity, I think of nearby.
Nearby, but not my twin, just my neighbor, right? My roommates live in my house. My neighbors are in the vicinity of my house. Yeah? Well, they're syn addition. Yep. Good question. Okay, on to that bottom diagram. This is the last of our diagrams. By the way, this is my first semester giving this out like this. In the past, what I've done is given blanks all the way around the diagrams and on the arrows. And I've had students take down the reagents as we go through class, because I believe writing this stuff down is important to you. So my recommendation is try to be able to do this by memory. Try to recreate these 12 reactions by memory. And start by just saying, I know I've got 3 sets of 4. And I've got 4 that involve a halogen. I've got 4 that involve these alcohols. I've got 4 that involve everything else. It's going to take you time. It's going to take a lot of time. Are you guys still spending 12 to 16 hours outside of class a week on this class? Because if you're not, I have an activity for you that can help you do that. Rowan.
So are we gonna need to know like both reagents, like for example on this addition where it has the or, we need both of those, or can we get away with just?
You should be able to recognize that both would do it. Because there could be a multiple choice question that says one of these, and you'd have to know that both of them do the same thing. Huh? It won't say or, yeah. All right, these last 4 reactions. Let's start on the top right again. So we're taking this alkene. Do you guys notice that this is a different alkene than the alkenes in the 2 diagrams above it? This is a structural isomer of the alkenes we were just working with. This alkene is tri-substituted as opposed to the di-substituted alkene we had before. We are looking at oxidative ozonolysis, otherwise called oxidative cleavage.
Is that the top right?
Top right. The existence of oxidative ozonolysis implies there's also reductive ozonolysis, and that's the one on the bottom right. But first, I want to point out the possibilities of what oxidative ozonolysis can form. So this cleaves a carbon-carbon double bond. All of the other groups were just adding across the carbon-carbon double bond. This is going to cleave the carbon-carbon double bond and create 2 carbonyls. In fact, when you're predicting these reactions, you can really just redraw the starting material, elongate that carbon-carbon double bond, and then erase it in the middle and draw in oxygens to make carbonyls. However, any vinylic hydrogens get oxidized to OH, carboxylic acid. Do you remember that ox in that box? That was not supposed to rhyme. We can put ox in parentheses to abbreviate that we're oxidizing something, and that's what we're doing. We're removing a bond from CH and we're replacing it with OH. So what the heck is this word? You might remember this from NMR. Something carbon. 4.5 to 6.5 ppm. This is bonded to an alkene. Vinylic is the group coming off of an alkene carbon, as opposed to allylic, which is adjacent to an alkene. Allylic, adjacent, vinylic, on it. So the possibilities that can form, well, we can see from here, if there are no vinylic hydrogens, it can form a ketone. If there's one vinylic hydrogen, it forms a carboxylic acid. I want to give you guys another example of what can happen with oxidative ozonolysis. So here's our starting material, a different one than what's in the diagram. Remember I said that you can just take that carbon-carbon double bond and elongate it, because what you're going to do is cleave it and make carbonyls. So here's my carbon-carbon double bond. Cleave it, make carbonyls, and then because it's oxidative, if there are vinylic hydrogens, they get oxidized into a carboxylic acid. Here's a vinylic hydrogen. So that vinylic hydrogen gets oxidized to form a carboxylic acid. Here are two vinylic hydrogens. Both of them get oxidized to form carboxylic acids. And this compound, you all know. Do you know it, though? Well, those are good words. It is a dicarboxylic acid. It's in your sodas, it's in your beer, it's in your champagne, it's in your blood. Close. It's the protonated form of sodium carbonate. This is carbonic acid. And when you shake up your soda and it fizzes, that's because all the carbonic acid is decomposing into water and carbon dioxide. So the example I gave you on that diagram shows that you can make carboxylic acid and ketone. There are models where you could make two ketones. There are models where you can make two carboxylic acids. But if you ever have this terminal alkene, it gets oxidized into carbonic acid, and carbonic acid decomposes into carbon dioxide and water. In fact, I was at a wedding once, and they were like only serving champagne, and my stomach was getting so acidic from all the champagne. So I went up to the bar, and I got a little stir stick, and I just got all the bubbles out. And it went flat because I decarbonated it, but I also deacidified it. It was less acidic because I had pumped out all of that carbonic acid by decomposing it. The more you know. Okay, the reaction underneath is reductive ozonolysis. Rowan, you asked earlier, do we need to know that syn-diol addition can be osmium tetroxide or potassium permanganate? You do, because oxidative ozonolysis doesn't have to be ozonolysis. It can be oxidative cleavage with potassium permanganate. And the difference in how we use potassium permanganate, I think I put it on here. I did. When making the diol, potassium permanganate, cold. Like you did it yesterday at room temperature. You didn't boil it. To do oxidative cleavage with potassium permanganate, hot. You have to boil it. It has to be given a lot of energy to do that oxidation. Reductive ozonolysis. It's still a type of oxidative cleavage. But vinylic hydrogens are unoxidized. This means that we're able to make ketones and or aldehydes. And the model that's given shows you how you form a ketone and an aldehyde. In the example that we were looking at up above, O3 with a reducing agent would make one aldehyde plus formaldehyde. Formaldehyde CH2O. Two last reactions. Yes?
What is it called? Ozonolysis. What is ozone?
Ozone means ozone. Do you know the chemical formula of ozone? Okay, that would help. Oh, I haven't written it on the board. Ozone is O3. So ozonolysis, hydrolysis, solvolysis just means reaction with ozone. The structure of ozone is an interesting structure as well. It's a Zwitter ion. You've never seen the structure of ozone? Oh. A Zwitter ion. A Zwitter ion is a neutral species that has two formal charges. A net neutral, but with two formal charges. Or more, maybe. Okay, second to last reaction, epoxidation. You can see that over the reaction arrow is MCPBA. That stands for metachloroperoxybenzoic acid. You don't need to know that, and you don't need to know what its structure is, but I'm going to show it to you anyways. It's not a carboxylic acid because it's not carbonyl bonded to OH. It's a peroxide version of a carboxylic acid. Remember that peroxide is that OO bond. So it's a peroxide carboxylic acid, a peroxy acid. And MCPBA, or any peroxy acid, in general, CO3H, it has that extra oxygen that it donates to the alkene to make the epoxide. And when it's done in that reaction, it becomes a regular benzoic acid. So after epoxidation, MCPBA becomes MCBA, metachlorobenzoic acid. It gives away one of its oxygens from the peroxide group. If you're catching on, peroxides are useful in oxidation reactions. Look at hydroboration oxidation. The oxidizing agent, hydrogen peroxide. Look at diol addition with osmium tetroxide and tert-butyl peroxide. Peroxide is an oxidizing agent. And then down here, this peroxy acid, an oxidizing agent. Because the epoxide is a three-membered ring that reacts just with the two carbons of the alkene, there is no carbocation intermediate. And the oxygen has to sit on one side or the other of the alkene. The oxygen can't be both above one carbon and below the other, because that would not allow for the oxygen to actually bond to both of them. So the epoxide is always synaddition, one side or the other. The last reaction, what would you name it? On the top right. Hydrogenation. This is something that you guys will be doing in lab next week. Of course, we could call it H2 addition. Hydrogenation uses PDC, which is spoken as palladium on carbon. It's a catalyst. Palladium catalyzes breaking hydrogen bonds, breaking hydrogen molecules. It's a terrible thing that we call them hydrogen bonds. That's not what I meant. Palladium helps break the H2 apart. Carbon, or charcoal, is just serving as a molecular scaffold. It is helping facilitate the interaction between carbon and hydrogen, palladium and hydrogen. We can't see it in this reaction, but this is also a syn addition reaction. And I'll give an example that demonstrates its syn addition. Once again, 1,2 dimethyl cyclohexane creates 2 chiral centers. The hydrogens form dependent on each other, syn addition. It's hard to tell that it's syn addition in this example because no chiral centers form. 12 reactions, 12 sets of reagents, 12 functional groups that can be formed. Actually, no, less than 12 functional groups, because a lot of them, yeah, you're right. 12 reactions, but I did combine haloether and halohydrin as basically the same thing. And actually less than 12 functional groups, because there's 3 different ways to make an alcohol. All of them consuming a pi bond in one way or another. The oxidative cleavage is perhaps the strangest one in how it consumes the pi bond. There are 2 things that I have seen in my years of teaching. One, God, that made me sound so old. Students really struggle with figuring out how to use these reagents without understanding how they work. I see this a lot. Students will try to look at a reaction and plug in a reagent, or sorry, look at a starting material and reagent and try to figure out the product missing. And they'll do it by trying to solve the mechanism. How do these reagents work together with the alkene to help me predict the functional group? I gotta tell you, that can be really challenging, and it limits your ability to actually apply it. So one of the first things I want you to be able to do is utilize a reaction diagram like this. This is one way of doing this. When I was in OChem 2, I actually realized how many reactions from OChem 1 were important that I needed to learn. So I made an Excel spreadsheet. I said, what functional group do I start with? What reagents do I add? And what functional group do I end with? And the time it took me to build that table was time spent studying, recognizing the reagents, being able to relate starting material functional group to product functional group. It helped me connect these. So I want you to be able to look at reagents and products and be able to just apply them. So that's what this first activity does on the backside. It has these blanks where you need to figure out what reagents are necessary, what structures are missing. On the top, notice how you're given an alkene. And you're given 3 different products without reagents. You need to fill in what reagents are necessary to get those products. Each of the reactions shown has 1 stereoisomer shown, 1 stereoisomer missing. You need to predict what is the missing product, what is the missing stereoisomer. The one reaction going to the left gives you the reagents. You need to predict the 2 products that form. On the bottom, it's a little bit different. On the bottom, you are given 2 different products that come from the same unknown starting material. You have to figure out a starting material that allows for the formation of both of those. And once you've determined that, figure out how that starting material or what product that starting material will form in the other 2 reactions. This is a puzzle. I hope you treat it as such. Have you ever tried to solve a puzzle by just brute force memorizing it? Doesn't work, right? Like, you can imagine the picture on the front of the puzzle box, but you can't memorize how the pieces are going to come together. You don't know, because every puzzle is unique. You cannot brute force memorize your way through this. You have to be familiar with the reagents and the functional groups. What's the difference between memorization and familiarization? Practice. That's the only difference. You can memorize the bones in the body, but until you familiarize yourself with pointing them out, memorization doesn't do you any good. You can memorize these reagents, but until you familiarize yourself with how they appear in different reactions, they're never going to make sense. So where do you get the practice? How are you going to practice applying these? Tell me. Where? Active's got practice problems. Active also has homework problems that has you apply these. So go do your active homework. Go do the practice problems on active. Where else? My old study materials. My homework, the homework that I made. Go do those. Where else? Practice exams. Go look at the final. Go look at how you're expected to apply this on the final exam. When we come in tomorrow, this is your homework tonight. When we come in tomorrow, we're going to fill these in. Before I start the recording, I'm going to have you come to the board and answer one of them. Or maybe not. If you don't want to, I won't force you this time. So we'll start with applying this to a roadmap tomorrow, and we're going to spend the rest of tomorrow doing mechanisms. So come prepared to ask questions about mechanisms. Enjoy the rest of your day. The rest of the time is yours.
Thank you.
See you tomorrow.